Hello all, welcome to the webinar series of IEEE Joint MTT AP EMC CAST chapter. I am Dr. Noshirwan Shoaib. I am the chair of the chapter and also serving as associate professor at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMMS, at National University of Science and Technology, Islamabad, Pakistan. So we're located in Islamabad. Islamabad is the capital of Pakistan, is among the beautiful capitals in the world as well. It has both a business hub and the natural beauty, and it is a place where we will conduct Pakistan's first dedicated RF and microwave conference next year in November 2021, titled as First IEEE International Conference on Microwave Antennas and Circuits, ICMAC 2021. And I hope to see all this over the year to host you in Islamabad. National University of Science and Technology has several campuses, and this is a bird's eye view of the Islamabad campus. It is a very well managed campus, and the Research Institute for Microwave and Millimeter Wave Studies is shown here. So RIMMS is a dedicated postgraduate institute that offer master and PhD degrees in electrical engineering with a particular focus on RF and microwave. We have foreign faculty as well as we have specialized lab, including the anechoic chamber, which work up to 40 gigahertz for antenna characterization. We have an electromagnetic compatibility and electromagnetic interference lab, yes, that is used for the coursework as well as for compliance testing. We have the micro research and antenna lab and PCB fabrication lab under one roof. The idea of having all these facilities under one roof is to provide an opportunity to the students so that they can have a hands-on experience, and afterwards it will help them during their career as well as for in their higher studies. So we started the webinar series in March 2020 in view of pandemic 2019. And this is our 23rd webinar, and we're very pleased to host distinguished Professor Atef Elsherbeni from Electrical Engineering Department, Colorado School of Mines, USA. Dr. Atef Elsherbeni is also the IEEE APS Distinguished Lecturer. The talk of the title is Recent Developments in Computational Electromagnetism Using the Finite Time Difference Method. A brief words about Professor Atef. So Professor Atef is currently with the Electrical Engineering Department, Colorado Schools of Mines, USA. He is the editor-in-chief for ACAS Journal, a past associate editor to Radio Science Journal, a past chair of Engineering and Physics Division of Mississippi Academy of Science, a past chair of Educational Activity Committee for IEEE Region 3 section, the Journal Chair for 2014 APS URSI Symposium, the President of ACS Society from 2013 to 2015, and IEEE APS Distinguished Lecturer from 2020-2022. Dr. Elsherbeni is also the Fellow of IEEE ACES, and it's our great pleasure to host him today. So without any further delay, I request Professor Atef to please proceed ahead and start the webinar. Over to you, Professor Atef. Thank you.
Thank you.
Yes, okay.
You all see my screen?
Yes, I can see you and your screen as well, and you are live now. You may continue ahead. Thank you very much.
So good evening, and thank you all for inviting me to make this presentation. I hope it would be beneficial for any one of you, and I have so many topics that I'm going to go through them very quickly related to computational electromagnetics using the finite difference time domain method. And feel free to communicate with me later on if you need any additional information or clarification of any of the slides that I'm going to present today. So basically, I'm going to look into how we develop a computational tool to solve our electromagnetic problems. And today, electromagnetic problem is not only electric field and magnetic field. There are many other circuit components, active and not active element, linear and non-linear element that can be integrated into a complete design. And the emphasis in my talk here is not only to show you how we calculate the electric and magnetic field, but also how to include some circuit element, linear and non-linear, into the computational tool that is basically based on Maxwell equations. We all know that most of our electromagnetic simulators start with Maxwell equation, whether it is in integral form or in differential form, as you see it here. And most of the well-known methods that we know right now are basically mist of moment, boundary element, finite integration, finite element, or finite difference, or finite volume, or finite element. All those well-known techniques can be implemented in time domain or in frequency domain. So today I'm going to focus only on finite difference in the time domain. Another talk could deal with finite difference in frequency domain and so on. Mainly I'm going to use the differential form of Maxwell equations, and at some times we are going to use some of the integral form of Maxwell equations in order to be able to extract some parameters that we needed to simulate some component in the simulation itself. So with this, basically, we know that Maxwell is the one who basically put about 22 equations to control E and H, and those 22 equations have been casted later on in just 2 curl equations and 2 divergence equations. In the finite difference time domain technique, the way we arrange the field components allow us to basically not to address the divergent equation and only deal with the 2 curl equation as you see them here. These are the 2 curl equations, and we choose to use them in a much more complete form. In other words, I'm adding here electric conductivity of any material in the domain, any impressed electric current, any magnetic conductivity, any impressed magnetic current. Of course, magnetic current is basically a non-physical component, but can be used for the simulation in certain problems as well. The conductivity, magnetic conductivity or electric conductivity, are basically representation of the losses that can happen in the material. For example, permeability, I can represent it in terms of a real value of the permeability, and the losses can be represented in an equivalent sigma m. The same thing goes for the permittivity of any material in the simulation domain, can be represented by a real number, and its imaginary component or its losses is represented in the sigma e, or the electric conductivity. Now these 2 are 2 curl equations. So, and we're going to deal with Cartesian coordinates in this presentation. We have other developments also that we have done in cylindrical and spherical coordinate system, but today we are going to focus on only Cartesian coordinates. So in Cartesian coordinates, we can expand those 2 curl equations into 6 equations like this, and we'll keep the derivative with time on one side, which is the left side, and on the right side is basically all the field components that are either represented there, like Ex or Ey or Ez, or their derivative with respect to the spatial coordinate, which is X and Y and Z. The same thing we can do it for this curl equation, and you can easily see that we have now 6 scalar equations. Each one of them is one differential equation, first order differential equation. But we also notice that we are challenged here to be able to solve 6 unknown components, Ex, Ey, Ez, and Hx, Hy, Hz, and all those 6 components are basically integrated into these 6 equations, and we can separate any one of those equations or combination of 2 equations to solve for a single value. So we have to solve all of them at once. So with this, and with the way we are going to do it, is that we are going to look at our computational domain. We are going to assume that we are going to start the domain with discretizing it into cells. And here is, for example, a general cell inside a computational domain, which is represented here within the boundaries that determine the domain boundary. The general cell is identified by the indices I, J, K, I for the X direction, J for the Y direction, and K for the Z direction. The first cell is going to be identified by 1, 1, 1, and the last cell in the computational domain will be identified by NX, NY, NZ. So knowing that we have NX cells in the X direction, NY cells in the Y direction, NZ cells in the Z direction. The multiplication of these three numbers will give us the total number of cells in the computation domain. For each individual cell, we basically need to solve for 6 unknown equations. So basically, if we have a domain that has 100 by 100 by 100, that's basically 1 million cell, and we have 6 unknown for each cell, then we have 6 million unknowns. And the time domain solution is basically steps through time. So basically we'll go with time equals 0, and we increment the time and keep doing this. And usually we do this for about 1,000 times or 2,000 or 3,000 times. So you can imagine how many times we need to solve those 6 equations, those 6 field components for each of the 1 million cell in this domain. So it's a very lengthy computations, but it's very easy, as I'm going to show it to you, that how we cast all those equations and how we manage to be able to solve this very efficiently. But before we go into this, imagining that any cell like this cell here, that's basically described here by the node IGK, and we need now to associate the 6 unknown field component with this node IGK. So the way to do it is to look at all the edges of the cell that are connects to this node, and for those edges, at the middle of those edges, we define the electric field component. For example, for this edge in the middle, we define EX, in this edge we define EY, in this edge we define EZ. And then we look at all the faces that connect at this node. So we can see this front face, this bottom face, and this side face. Those 3 faces are connecting at this node. Now we take a vector going into the middle of each one of those faces, and this vector represents a magnetic field component. For example, for the bottom face here, the middle of it, you can see a normal to it going into the cell, HZ component. Here we have HX, and here we have HY. So those 3 magnetic field component and those 3 electric field component are the ones that are associated with the node IGK. You can see in this figure some other field component are not identified by IGK because they belong to other nodes in this arrangement here. So this is how we define our electric and magnetic field component, and with this definition, which is basically proposed by Yi, that allows us to ignore completely the application of the divergence equations, because the ways they are set up right now allow us to use only the 2 curl equation for Maxwell equation. Now we also need to discretize the domain and define our geometries, and geometries are going to be defined in terms of permeability, mu, and permittivity, epsilon, and sigma E and sigma M. Any component of the permittivity is going to be located at the same position where we have the electric field. Any component for the permeability is going to be positioned in the same place where we have the magnetic field. The same way, sigma E is going to be positioned with the electric field component. Sigma M will be positioned with the magnetic field component. So now let's go back to the 6 equations. So now we know that where are going to be the field component located, where are the epsilons and mu's and sigmas are located, and we need to look at how we can solve all those 6 equations. So we're going to start with only one of them, and we develop what we call it updating equation. In other words, equations that we can program it, put it in the computer, and with it we can try to figure out a relationship between electric and magnetic field components. We notice that these are first order differential equations. Sometimes we differentiate with respect to space, or sometimes we differentiate with respect to time. So we need to translate this partial derivatives, as you see it here, into a form that we can do it in the computer. And the way to do it is to use the central difference approximation for any function. So if I have a function here, a function of x, f is a function of x, and the derivative of the function I defined with this prime here, then I need to evaluate the function at x plus delta x over 2 and subtract from it the function f at x minus delta x over 2 and divided by delta x. If I do this, then I get a very good approximation for the derivative of the function with respect to x. So what is basically involved here is that if I need the derivative of the function, I need to evaluate the function at two positions, and the evaluation of the function at these two positions is going to allow me to evaluate the derivative. So basically, if you look at the x-axis here, if I need to get the derivative at the position x, I need to evaluate the function at here, x plus delta x over 2, and at x minus delta x over 2. And from these two values, I divide them by the difference between them. I divide them by delta x, that gives me the derivative. So that's basically the form here. And I represented this equation here now in terms of I and j and k. And I plus 1/2 and I minus 1/2. The 1/2 is basically indicative of the position of the field component that basically dictated by the Yee cell. So this is the derivative with respect to x. We can apply it for derivative with respect to y, with respect to z as well. The derivative with respect to time is going to follow the same formulation, except that the superscript here, n, which would be an indicative for the time instant, I'm going to add to it 1/2 delta t, and here I'm going to subtract 1/2 delta t and then divide by delta t. So now I have established an equation here, an approximation here for the derivative with respect to time and the derivative with respect to space. We can use this, for example, we're going to start with one equation like this. I have here derivative with respect to time can be translated to this approximation here. I have here derivative with respect to y, which would be translated to this formulation here. Derivative with respect to z is going to be translated to this term here. Now, since I am differentiating this term with respect to time, and this is n plus 1 and this is n, then this derivative is being evaluated at n plus 1/2. Then every term on this equation on this side should be evaluated at n plus 1/2. And you see that this term, as represented by its approximation here, is evaluated at n plus 1/2, n plus 1/2. The same thing for this term, n plus 1/2, n plus 1/2. Now I need to evaluate Ex at n plus 1/2 and J, which is the impressed current, at n plus 1/2. This is very easy because we can evaluate it at any time, so we can put it here at n plus 1/2. But Ex, since I'm going to evaluate H at n plus 1/2, and n is being evaluated at n and n plus 1, it is better to approximate Ex here that needs to be evaluated at n plus 1/2 by the average of its value from n plus 1 and n, and take this average and put it here. So this way I have all the electric field components are evaluated at n and n plus 1 and n plus 2. All the magnetic field components are evaluated at n minus 1/2, n plus 1/2, and n plus 3/2, and so on. Now, if I look at this approximation of this differential equation, I see that my future term, which is Ex at n plus 1, is existing here and existing here. So I need to take this to this side, take this term to this side, put all the coefficients that are related to the future term of Ex on this side. Everything else that's a previous time in terms of n or n plus 1/2 on this side, and you can easily see that I have, this is just a constant coefficient, and so on. So I can manipulate this formulation into something like this. The new value of Ex at a new time is a function of the value of Ex as the previous time, plus a coefficient times the value of difference between each component as a previous 1/2 delta time, and another coefficient times 1/2 of delta time for Hy, and then another coefficient for the impressed current at 1/2 delta time previously. We notice that all these coefficients are basically not dependent on time. They do have only delta t, which is fixed. They have sigma e and epsilon and mu in another expressions. So basically I can associate all these into certain coefficients. So I can recast this equation in a general form like this. Ex at n plus 1 is going to be a coefficient times Ex at n plus another coefficient difference between Hz, another coefficient difference between Hy, another coefficient times the impressed current. And these coefficients can be evaluated only one time before I run the time iteration over the index n. So now this differential equation is approximated with a very simple equation here that has multiplications of coefficients addition and subtraction, and the coefficients, they don't have anything other than division and multiplications. Very simple equation that we can program it in the computer. Anything we have done for this equation, we can do it for the other 6 field equations. And once we do this, we are going to end up with 3 updating equation for the electric field as you see it here. This is for EX, for EY, and EZ, and these are corresponding coefficients that you see them here. And if I look at the coefficients for all those 3 equations are basically here, they are very simple equations that we can compute. The same thing we do it for the magnetic field component. We can end up with 3 equations like this, and these are the corresponding 6 corresponding coefficients for the E component and H component. So the formulation of the method is very, very simple. Just basically to implement those 3 equations into a code and evaluate the coefficients one time, implement those equations with their corresponding coefficients, and basically iterate over all those 6 updating equations. We call them updating equations. So the setup of the program is like this. We set up the problem space and we define the parameter. Definition of the parameter is nothing more than defining what would be the increment in X, increment in Y, increment in Z, what would be delta T, where are the magnetic, the epsilon and mu is going to exist according to the objects that we have, or the circuit elements, as I'm going to explain later on. And then we calculate all the coefficients that are existing in this slide and this slide. We calculate them only one time here, and then we start a time iteration or a time loop. We update all the magnetic field component at n plus 1 delta T, 1/2 delta T, and then the update all electric field component at n plus 1 delta T, and then apply some boundary conditions so we don't end up with an infinite domain, and then increment the time by n equal n plus 1, and keep iterating here. Each time we output some data, and we can come up with a stopping criteria. We stop the simulation. Once we stop the simulation, we take the output data that are in time domain and process it to get also a frequency domain response of the simulation that we conducted. So the process is very, very simple. Writing a program is also very simple. But the key point is to define the parameter in such a way that it would be a suitable parameter, so we don't end up with any dispersion, any instability of the code, or any errors that are going to be hidden for us and will not be able to see it. So with this, basically everyone would be able to write code to evaluate those electric field, those magnetic field, and that's very easy, and there are so many programs available for computing this. My presentation is going to focus on how to use this formulation also for linear circuit element and non-linear circuit element as well, because this is not common in the literature and you don't see much publication on this. So basically, we can look at a voltage source with internal resistance Rs. I can put it between 2 nodes. I can assign a voltage source here and internal resistance here, and I can do a formulation that will update the electric field between these 2 nodes, which is easy here. And that updating equation, I can cast it in the same form as the updating equation of EZ in a traditional cell that doesn't have a voltage source. You can see it is the same. The future E is in terms of previous E, coefficients times magnetic field in the Y direction, coefficient times magnetic field in the X direction, and then a source. The only difference is that those coefficients are determined here, and they are going to have the internal impedance or resistance Rs here. So implementing or inserting a voltage source with internal resistance in a finite difference time domain code is being implemented in a very, very simplified form, and the only thing to do is basically to calculate the proper coefficients for the field component between these 2 nodes, and that's all what we really need to do here. The same thing we can do it for a current source with parallel resistance. You can see the same form of the updating equations, and we can do the same thing for an inductor between 2 nodes. You can see the same form of the equations, and these are the coefficients, and also for a capacitor as well. So all these elements, some of them are active, like current source and voltage source. Some of them are passive component, R and L and C. We can integrate them very easily in a computational domain that uses Maxwell equation to predict the performance of a circuit integrated with an antenna, for example. So to give you an example, let's look at this very simple simulation here. And we're going to use a sinusoidal waveform here because we can predict the results of a circuit like this, and we can see it. And everything you see it here in terms of results is not obtained by a circuit theory, is obtained by application of Maxwell equation based on E and H calculation. So I have here a voltage source with internal resistance and two conducting plates terminated by a resistance that's equivalent to the internal resistance of the source. So if I have a sinusoidal waveform, as you see it here in the blue curve, and basically amplitude is 1, and this resistance equal to the internal resistance, then basically this circuit works as a voltage divider. And the voltage across the resistor here is going to be 1/2 of the source voltage, which is exactly what you see it here in this figure. So that basically confirms that the implementation of the voltage source, implementation of a resistance in a finite difference time domain simulation based on Maxwell equation is producing the correct and expected result as well. Here is another example. If I put a capacitor, I put an input step function here for the voltage source. I also can generate an exact solution for the response of the voltage across the capacitance from analytical solution, and also the blue curve give me the sample voltage across the capacitor using finite difference time domain. You can see a perfect match between the two solutions as well. In this configuration here, we have an inductor. You can also see a very good correlation between the two solutions. And let's look at some more complicated structures. For example, a diode, for example. I need to represent the diode equation into Maxwell equation. So the way to do this is basically to look at the VI characteristic of the diode and convert the V into electric fields and convert the I into magnetic field, and then get the E and H relationship and insert it or represented in a standard form as we have for the updating of E and H. Once we do this, we can implement a diode in a circuit. And here is one example, a voltage source. A diode is connected between these two short plates. And you can see the voltage source that's going through the voltage source here. The signal is basically sinusoidal. The signal capture across the diode is basically terminated at one cycle. And basically you see here the clipping of the diode effect on the output results. Everything, as I mentioned before, is obtained using E and H field component, and then once we get them in time domain, we convert them to frequency domain, and we sample across the voltage to across the E field to get the voltage. We sample on a closed loop of the magnetic field to get the current as well. Here is another a little bit more complicated circuit where we have a capacitor and diode in series, and you can see the charging effect of the capacitor here due to a sinusoidal waveform coming from the voltage source. So here is the similar circuit, but the diode polarity is being inverted in the opposite direction. You can see the discharging of the signal going in the opposite direction. So these are some of the results that we can get from elements like this, and you would expect that the time domain results would be very, very good, correspond to what we expect. But we can also use the time domain simulation to predict the harmonic and non-linear characteristic of these elements. And the way to do this is basically, let's look at this very simple circuit, a diode and the resistance and the voltage source. We are gonna bunch in a 5 GHz signal here into the voltage source, and we are gonna capture the voltage across the output voltage here across the resistance. You can easily see that the voltage across the resistance here is basically according to the diode behavior here is represented by the red curve. And once we get these time domain results, we can convert it into frequency domain results, and we can get the expected result as you see it here. The ones that are represented by the blue color is based on a program that we called it, we developed this program based on finite difference time domain, we call it SIMS. And the purple color here is basically computed using ADS. So you can see a perfect match with these two solutions for this simple circuit here in the time domain. Now, if we switch or take this time domain data and convert it to frequency domain, we can easily see that we can see the fundamental signal here coming at the 5 gigahertz, and the harmonics are also being represented here as you see it from the capturing of the voltage across the resistor here. So the capturing of the voltage coming out of the voltage source give you only a 5 gigahertz signal that you see it here, and the capture of the voltage across the resistor shows the harmonic and then linearity characteristic of the diode that basically injected in the response of the voltage across the resistor. So this is all coming from a time domain signal or a time domain solution. We can predict time domain result, and we can also predict frequency domain result as well. Just to confirm that the frequency domain results that we have is accurate and good, we can compare it with EDS, and you can see a perfect match between the two results as well. So that's a very good technique. We can use it, and we can even use it for much more complicated circuit. A circuit like this, where I have a voltage source here, I have a low pass filter here, a diode here, and then basically a load here. The purpose of this low pass filter, which is being constructed by capacitor and inductor, as you see it here, is basically to prevent any non-linearity of the diode to come back to the voltage here. So basically, if I sample the voltage across the voltage source, I'm going to get only one signal at 5 gigahertz. If I sample the voltage across the resistor, I'm going to get all these harmonic as well. So that's basically what we have done with simple element like RLC, voltage source, current source, diode, and we can also do it for amplifiers. And if you want to simulate an amplifier, integrate it into a microwave circuit, for example, you need to convert the amplifier equivalent circuit and look at all its components and represents each one of those components in a finite difference time domain. The new component that you see it here is the dependent source here. So we developed equation also to represent the dependent sources in a finite difference time domain, similar to what we did with the independent sources. And here is an example of an op-amp amplifier with basically input voltage here represented by the red curve, and the output voltage here at port 2 coming from the finite difference time domain with the blue curve, and the circles here represent the analytical solution or expression from circuit theory based on this. You can see a perfect match here, and if you convert these results into frequency domain, you can see the input voltage at this level and the output voltage at this level. You can see approximately about this is 20 dB minus 25, that's about 45 dB gain using this amplifier here. We can also do a Mosfet circuit. The key point here is again to represent its equivalent circuit into the finite difference time domain. Here we see a dependent current source. In the previous example here, we have seen dependent voltage source. Both of them are being represented in a finite difference time domain equation, and the result of this simulation also give you a very good correlation between the finite difference time domain result and B-SPICE results for this simple circuit. And we also did a Bgt amplifier circuit, and an equivalent a representation of it give you again, as you see it here, going from minus 10 dB for the source, and the output port here is giving you about 35 dB gain. In addition to this, if we discretize the domain in a uniform discretization, sometimes it's going to be very costly and it's going to take so much memory on the computer. So we need sometimes to do a non-uniform discretization, and simply if you look at configuration like this, I can solve the problem with a fine discretization like this, but I'm going to use so many allocation in memory, I'm going to take much more time. Or if I do it a very coarse mesh like this, I'm going to end up with a solution that's not very accurate. But obviously, if I have smaller cell around this area where I have some variations and the coarser cell over here, I may end up with a number of cells here that's in between these two cases here, and I will be able to get useful results as well. So to show you how we do this, if this is the discretization of the coarse cell and this is the fine cell, we don't jump directly from coarse cell to a fine cell, otherwise we are going to create an interface that has numerical error. So we transition from the coarse cell to the fine cell in a region that basically transition with larger cell here, a little bit smaller than this one, a little bit smaller, until we reach the fine cell discretization. Implementing this technique, even here is another example where we have fine cell here, coarse cell here, coarse cell here. We can have two transition region and controlled by these equations that we have developed. So just to show you some examples, here is a microstrip batch antenna. The fine cell solution is basically the black curve, which is basically under the non-uniform discretization, the blue dash curve, and the coarse cell is basically the red curve. You can see if we use a coarse cell, the frequency is going to shift. We're going to have a little bit of difference. If you use the non-uniform discretization, we end up with basically very, very good accurate results with the fine cell. So what did we gain out of doing this? What we gain is basically, you see that the simulation time is being reduced tremendously from 33 to about 20. The number of cells that we have been using in the fine cell is about 8,000. And in the non-uniform cell here, in this case, it's basically 8,000 again, but you can see a saving in time. In another simulation, as you see it here, you can see that the number of cells goes from 720,000 cell to 228,000 cell. At least 3 times smaller domain. And you can also 3 times faster execution time. And we're getting perfect results because the result of the non-uniform here for this configuration is simply overlapping on the fine grid solution, and the coarse cell is basically showing you some differences here. So with the non-uniformity, also we can, it allows us to be able to have a solution that's more efficient in terms of usage of time and memory on the computer as well. In addition to this, we can also implement a body of revolution finite difference time domain in which configuration is basically rotationally existing around, we have an axis of rotation, and this rotation is completely rotated from 0 to 2 pi or 0 to 360. In such a case, we can represent the phi variations in modes, and we can eliminate completely the third dimension, and we can do the solution for a body of revolution in a 2-dimensional domain. We extended this solution to integrate it into, to basically allow it to use a sectoral rotation. And the sectoral rotation that I describe is basically, instead of having a full 2 pi rotation, we can have sectoral rotation. For problems like this that has 4 rotations are represented by some examples here. But if I have an example where the rotation is only characterized by an angle from -v1 to +v1, can I also develop a formulation that I can use a 2-dimensional formulation for it rather than 3-dimensional? And the answer is yes, because I can look at the phi variation here with the derivative here, and I can represent it in the 2-dimensional grid that's going to be on only in one plane here, rather than the entire rotations. And that derivative here is going to represent it by the variable m here. And once I do this, my updating equation here is going to be in this form, where I have a variable m. And this variable m is nothing more than a function is going to depend on the angle of the sectors that we have. And once we implement this, we can update the, or we can update our magnetic and electric field component. In this situation, we are dealing with cylindrical coordinates, and we are dealing with all 6 field components on a 2-dimensional plane. And to implement this on this configuration here, for example, instead of solving all the field components in the entire domain, we solve them only on this plane. And to show you that the solution is producing accurate results, we looked at the resonance of this cavity here. We looked at all the frequencies coming of the from the finite difference time domain, and their normalized values are here, and their exact values that are coming from an exact solution is here. So you can see that for these two modes, they are going to be exactly the same modes. We also looked at many other combination of cavities like this, and you can see all these modes and their comparison again with the exact solution are predicting very, very good examples. So what we have done here is, instead of solving the entire three-dimensional domain, we solved the problem by only solving a two-dimensional problem, but this two-dimensional problem has the sixth field component in cylindrical coordinates. Also, some materials, they do have some objects, they do have material that does not have constant parameters as a function of frequency. For example, human tissues, for example, skin or brain tissue or something like this, if I change the frequency, then the permittivity of these tissues are going to change. So how are we going to implement this kind of permittivity variation and potentially for other objects that have permeability variation in the finite difference time domain, in which I am setting up the permeability and permittivity at certain position with certain values. So for this, we really need to develop another updating equation that is based on dispersive kind of formulation. And in this dispersive kind of formulation, basically, we look at one example here. For example, in this example here, the permittivity, the real part of the permittivity is changing. The imaginary part of the permittivity is changing across the frequency and represented by this equation here. So the permittivity is a function of frequency. And if the permittivity is a function of frequency, basically, we need to figure out a way to be able to represent this equation into the finite difference time domain equation. So we did this and we integrated a dispersive type formulation for those kind of tissues or those kind of materials that are basically dispersive kind material because their characteristic properties change as a function of frequency. And we tested the solution with an exact solution for a dispersive sphere. A sphere here is basically characterized with permittivity, real part changing like this, imaginary part changing like this. We did the finite difference time domain solution and the analytical solution, and you can see a perfect match in the RCS in the two different planes, theta plane and theta phi plane like this. So this is basically what we did, and the reason we did this because there are so many applications right now in terms of cellular phones and smart glasses. For example, we are using it, and we're using Bluetooth, we're using Wi-Fi, and we're using all those frequencies on multiple of them, using antennas, for example, in a cell phone closer to a human head that basically use a couple of antennas. Each antenna is working at a different frequency. So we looked also at the simulation of the human head next to an antenna here, mimicking basically a cellular phone. And for this, we use discretization of the, not the discretization, representation of the permittivity of the human tissues in a Debye model in three terms like this. And we developed this formulation and this three terms for different types of a human cell in this publication here that we published in 2001. When we did this simulation recently, we chose only 8 cells of the material that describes the human head, and for all these 8 cell, different tissues, we have the material properties that describes them in variable permittivity as a function of frequency. So we use this in the dispersive code to evaluate what we call it SAR, or specific absorption rate. Is basically how much is the electromagnetic wave is being absorbed into the human head. And in addition to this, we use a bioheat equation in which we can take the SAR values that we calculated from the time domain simulation and predicts the temperature distribution in the human head based on the excitation with the electromagnetic wave. So when we do this, we started with 8 tissues, And the discretization for one application we use 0.9 millimeter cell size, and in another application we use 2 millimeter cell size. When you use mimicking a cellular phone closer to a human head, we needed an antenna that work at multiple frequencies. So we use the dipole antenna and with two parasitic elements next to it so that we can force this configuration to work at 900 megahertz and 1.5 gigahertz. Those are two of the bands that are commonly used in some of the cellular phones. So we put this antenna next to the human head. We calculated the SAR using this equation, and we calculated the temperature rise using another differential equation very similar to the differential equation of the 6 field components. And based on the calculations that we see that the maximum temperature rise in the human head around 900 megahertz or around 1.5 gigahertz are basically represented by these three curves here or these three curves here. So you can see from this simulation that after 20-minute illumination of this combination of the antennas that mimic a cellular phone, that basically constitute about 0.15 centigrade increase in the temperature inside the human head, or about 0.25 or 0.27 centigrade temperature rise. I should mention here that when we ran the simulation, we ran it for 6 different frequencies. We ran the finite difference time domain simulation only once, and from the one simulation in finite difference time domain, we predicted the solution for all 6 frequencies as you see it here. So for these results, you can see here, over here, you can see the at 900 megahertz and 1.5 gigahertz the SAR distribution. The antennas here closer to this left ear, so that most of the fields are going to be closer to the antenna. And you can see the temperature rise in the human head also represented here. You can easily see that the temperature rise at 900 megahertz is distributed in the head much larger and stronger in a much larger area and stronger than what you see it here in the 1.5 gigahertz, which is also being reflected in these figures here. This is basically temperature rise about 0.27 centigrade, and this is about 0.15 centigrade. We did also the simulation where we have an eyeglasses that has an antenna now transmit and receive, and basically implemented on top of a human head model. So the eyeglasses, we said, for example, to be practical, we may be able to put the antenna here in the bridge, and sometimes we put the antenna in the left arm of the glasses. So this is the eyeglasses that we simulated in the finite difference time domain program. We simulated everything, the lenses, the plastic material, and the hinges that are metal, and also we put an antenna here at the left arm or antenna in the bridge, and any one of those antenna is a combination of dipole antenna and parasitic element to give us 2 frequency of operation, 2.4 and 4.9, that are mimicking cellular phone operation or Wi-Fi operation. So we did the simulation, this simulation for the 8 cells, as we mentioned before, and with 0.5 millimeter discretization of a human head model. And basically we looked at the performance of the antenna in the left arm or in the bridge in terms of operation at these 2 specific frequencies, and you can see a very perfect operation at those 2 frequencies with and without the head. And then we put the head inside, or we put the glasses on the head, and we looked at the radiation pattern, and we looked at the SAR distribution and the temperature distribution. In this configuration here, we have the antenna on the left arm. You can see here that the SAR is closer to the left arm, and the temperature distribution is also closer to the left arm, as you see it here. The radiation pattern is definitely going to change, whether if you have the radiation pattern without the head, is basically the blue curve, and once you have the antenna, the glasses on top of the head, the radiation pattern is going to be different, and you can see the radiation is away from the head more than the radiation towards the head itself. So this slide here, where the antenna is on the arm of the eyeglasses, this slide here represents the situation where the antenna is in the bridge between the lenses, and you can see the SAR and the temperature distribution as well. And you can see the temperature rise for 2 different frequencies here, 2.4 and 4.9 gigahertz. And you can also see here the improvement or the efficiency of the code that we have developed for all those frequencies that we have evaluated around 2.4 and 4.9. We have about 60% efficiency saving in time when we use the dispersive code rather than using a traditional finite difference time domain that we can run it at each individual frequency, because at each individual frequency the permittivity has a fixed, has a certain permittivity. So another things that we should always recognize that the use of finite difference time domain is very, very good, because it can provide us some animation and visualization for the field variation in the domain that we are simulating. For example, here we have a slab and a plane wave propagating from down up, and you can see at different time steps how is the plane wave is generated in the slab. Here is another configuration with the dielectric sphere. Also plane wave propagating from down up, and you can see the propagation and the field distribution inside the sphere and outside the sphere as well. We can also create some sort of animation based on the programs that we have generated, and this is just a snapshot of different field configurations in a dielectric sphere. Because we developed our code on also to work on the GPU, so the actual calculation is being run on the GPU. Here is one example in which we do the calculation on the GPU and we also do the animation on the GPU. So the GPU is being used to animate the simulation for a plane wave here hitting a dielectric cylinder, and at the same time doing the electromagnetic simulation. The performance of this two-dimensional simulation is basically giving us about 900 million cells per second execution. And I'm going to touch on this later on in terms of the performance of the finite difference time domains that we have created. So basically, we look at the finite difference time domain. Many years ago, we started with a finite difference time domain developed on a FORTRAN language. Then we switch it to MATLAB operation, and with the formulation I just presented here, it became very efficient to use it in such a kind of formulation. And then we switch it to implementation on graphic cards. And this is basically the structure of the programs that we generated that has all these kind of objects, all these kind of circuit elements. And here is one example for a loop antenna on a dielectric substrate and a ground plane. But if I put a EBG structure under the loop, I can get the loop to operate. And basically, the amount of time that it takes to simulate this entire structure is 0.7 minutes, is the same amount of time that I simulate this structure without the EBG. The complexity here of the EBG did not add any additional time in the finite difference time domain simulation. But if you do the same thing on any other technique, you would end up with much more time and much more complex simulation. Here is another configuration for an RFID structure with a non-uniform discretization, and you can see the simulation based on finite difference time domain and HFSS is very comparable, and also compared to the measured results. Here is another printed monopole antenna, and here is a Vivaldi antenna where you have a very wide band application for the Vivaldi antenna, one element. And you can see all kind of results in terms of input impedance, bandwidth, and basically radiation pattern. Also dual polarized Vivaldi antenna, and you can see very wide band characteristics can be obtained with this finite difference time domain simulation. We can also look at the radiation pattern as well. We can use this technique also to predict the radiation pattern from arrays. Here is, for example, one element dipole antenna. We can extend it into 5 elements, and we can get the characteristic impedance in terms of the input impedance at each element and the coupling between the elements. And we can also assign the phase shift for each individual element post-processing after evaluating the time domain solution, and predict the radiation pattern for one configuration of the phase for all the elements. And if we change the phases, we can predict the corresponding tilt in the radiation pattern for the antenna array. Here is a much more complicated antenna array, and you can see the wide bandwidth characteristics that we obtained with this simulation. Now, going back to the performance of this code, how many million cells of the updating equation? That updating equation is basically 6 unknowns for each cell. So we measure the performance of the finite difference time domain in terms of how many 6 unknowns in each million cell is being updated in 1 second. So million cells per second execution or evaluation, which includes 6 million unknowns, is basically our performance. So you can see here the performance of different graphic cards. And those who are familiar with Microsoft computer, the small handheld Microsoft computer, gives you about 200, that has a very primitive graphic card that give you about 250 million cells per second execution. And based on the memory, you can only go to about 20 million cells. Right? And about 2 years ago, we managed to be able to execute up to 4.6 billion cells per second execution on a single graphic card and we can address about 220 million cells. So you can imagine 220 million cells, and the execution time is 4.6 billion cells per second execution. That's the performance that we have achieved so far. Now, we have computers now that has 2 of these graphic cards or even 4 of these graphic cards, and the performance is basically keep going up, and we managed to be able to simulate all the way up to 500 million cells and even above this. In addition to this, we build a code that would be very easy for students to use on multi-core and multi-GPU using the MATLAB toolbox. And some results here are shown in configuration where we have 6 physical cores, and basically you can see the performance improves from about 7 million cells per second in one core all the way about 30 million cells per second. And here is another configuration, another computer that has 16 physical cores, and you can also get about 25 million cells per second execution performance here. And on another computer that has 32, that's one of the AMD new CPUs, you can also reach about 50 million cells per second. All these improvement is being obtained by a simple, very simple command that you can implement in a MATLAB code that's very simple to program, but you have to use a parallel processing toolbox. We did also on the same kind of simplification on the 2 graphic cards, and you can reach from about 7 million cells per second to about 700 million cells per second with simple commands on 2 graphic cards. And 2 graphic cards also here that each one of them has 2 GPU processor, and you can also reach about 900 million cells per second. So these are very simple implementations. Students can do it using MATLAB code, but the real performance you can get it if you use or convert all your program into a CUDA and implement it on a graphic card. You can reach beyond 4.6 billion cells per second. So I think with this, I'm going to stop here. And I just would like to say that finite difference time domain is an easy method to implement, but there are still many, many new challenges in this technique to solve practical and challenging problem, specifically in spherical and Cartesian and cylindrical coordinates. I would like to point out that we have published the first edition of our book on finite difference time domain in 2009. And 2015, we added new features and new chapters, and we added also a code that uses CUDA and GPU for 2-dimensional evaluation. Would like to acknowledge the contribution of many of my former students who are now faculty members, and also people who are working in industry right now, and current PhD students working with me right now. So with this, I thank you very much, and I'll be glad to answer any questions.
Thank you very much, Professor Atef, for your very interesting talk. There are a few questions that I would like to ask these are the questions from audience and few of my questions. So the first question is regarding the simulation time. So the question is, if we use different CAD tools, so why we get a different simulation time if we use a CST or ADS?
Well, one thing that we have implemented in our code is a unified formulation. And our unified formulation and it's complete in terms of Maxwell equation, as I mentioned at the very beginning. Incomplete in terms of that we have all the impedance sources, or the electric losses, or the magnetic losses in one unified formulation that basically uses only multiplication and divisions, and we calculated all the coefficient before we start the time iteration. And when we do the time loop, we do a vector operation. We don't do cell by cell. We take the entire vector, entire three-dimensional matrix, multiplied by a three-dimensional matrix, multiplied by three-dimensional matrix. For example, in the updating equation that we have 6 unknown, Ex, Ey, Ez, and Hx, Hy, Hz. Each one of them, each one of those component is an unknown in the million cell, for example, in the million cells that we have. We don't go through each cell and evaluate Ex at cell 1, cell 2, cell 3. We take all the Ex field component in the entire million cell and evaluate it with one line of code in MATLAB. We do the same thing on the GPU. So our updating equations, Ex, Ey, Ez, Hx, Hy, Hz, are basically 6 lines in our development code to do the updating equation. That's why our code is much faster than comparable CST or HFSS or other codes as well. I don't know, does this answer your questions, or you need a little bit further explanation?
Yeah, I think that's what the actual question was. So I think you have answered this very well. So the next question is regarding your tool. So is your tool, your own developed code is open source, or is available in the commercial domain or not?
Our professional or semi-professional code is not widely available, but everything I presented here except the simulation of the amplifiers exists in a MATLAB code with the first edition of the book and the second edition of the book. Of course, the second edition of the book does have periodic boundary conditions, does have non-uniform discretization. It does have also GPU programming using CUDA. So if you have the second edition of the book and you go to the publisher website, you can download all MATLAB codes that basically all my students are using it for development and designing of antenna.
Yes, thank you very much. The third question is regarding if we have, for example, electrical large or object, spherical, cylindrical, so what you suggest in terms of simulation? So why in a typical, if you use a typical software, it takes a lot of time to simulate, or you need a very high PC or maybe a supercomputer to simulate that object. Similar is the case with the biomedical application. If you simulate a human body model in CST or HFSS. So it take a lot of time. So in the presentation you have mentioned about the human body model as well, and also some other examples as well. So how you correlate that commercial software with your own developed code?
Okay. I know for sure that when you start looking at commercial code and you ask for a human body model, for example, that's an extra cost. They don't give it as basically as a default item in the basic package. On top of this, so that if you can use a commercial code to do these kind of simulations if you pay the price for the additional features. On top of this, if you would like to have the commercial code, which are HFSS and CST right now, they do have codes that are running on GPU. We started this more than 20 years ago to run things on the GPU. And they started to run also this maybe about 15 or 10 years ago to run their codes on GPU and multi-GPU and multi-processor. For this also you have to have an extra cost because they don't give you the original package running on more than one CPU and it's not running on GPU. On top of this, the commercial package CST and HFSS, they run on a professional grade GPUs. All the simulation I showed it to you here are not running on professional grade GPUs. We use the consumer type GPUs that are being used by general public for gaming industry. they are at least 4 times cheaper than the professional types GPUs. So we're running our code with much more performance, and we're running it in a much lower cost hardware. On top of this, if you really need to get the full performance, which we have it from our SIMS package, we can run the entire airplane with multiple antenna on it in less than 20 minutes. The entire airplane, we can get the RCS in different directions with different frequencies in less than 20 minutes. Now, can we do this using MATLAB? That's why I hinted here on some of our work on using multi-core and multi-GPU using MATLAB Toolbox. You can jump from 7 million cells per second using CPU and MATLAB to about 50 million cells per second using MATLAB code and parallel processing toolbox. So the extra cost that come to you is basically to include parallel processing toolbox in MATLAB, use simple functions, and we describe this completely in a paper in ACES journal, how to update MATLAB code so that you can use parallel processing toolbox and you get the full functionality of multi-cores of your processor and multi-GPU or GPU that you have in your computer. And this is the most efficient and easier way to basically speed up code that you continue developing it with the students so that you can know exactly all what is being done there.
Yes, thank you very much. So if, for example, a student or researcher would like to simulate his, let's say, would like to simulate antenna or a human body model and would like to use your developed code. So what is the process to contact you or to get that code?
Usually we can make it available with groups that we are continuously working with them, and we have joint project or something like this. So I'll be glad to talk with you more about this, and we can try to arrange something that we can do it in the future.
That's perfect. So maybe this last question, not a technical question, but as you see in your slides, you have shown very extensive mathematics, and then at the end, student there also a code development. So for a student in RF and microwave, so how you motivate a student that he has both RF knowledge and also programming knowledge, or how he can adopt this field?
Even though we have commercial software packages that we can get the students to learn and to produce some result using it, they lack the knowledge of how these software are being developed. And because of the lack of this knowledge, sometimes they punch in some parameters and they get some results, and they are not going to be able to predict if these results are correct or not. So the best thing to do is to encourage the students to do some development on their own first, to get a feel of what kind of input parameters they should input into a code and what kind of accurate results they can expect. If they got this feel and this experience in a simple MATLAB code, for example, then we can upgrade them and tell them, now you can use this commercial software. Now you know how to integrate, how to put the right parameters for the problem. Now you know how to examine the results and predict if it is correct or not correct. So the programming experience for simple configuration first would be tremendously valuable for them to be able to use commercially available software with perfect execution.
Yes, very right. I think this also gives, I think all the listening students as well a motivation to start research in this area as well. So, Professor, with this, I would like to thank you very much for your very interesting talk, and I hope we see you again. We will be holding the next year the first dedicated RF Micro conference in Islamabad, and we will be happy to host you in Islamabad as well. and hope to see you at some other occasion. Thank you very much.
I just would like to tell you that the Distinguished Lecture Program extended our appointment for 1 more year. So potentially my appointment as a distinguished lecturer is extended to 2023 as well. So if there is any opportunity in the future, I'll be glad to visit and share many more presentation with you all.
Yeah, we will love to see you in the face-to-face mode in Pakistan, and I hope that we meet very soon. So thank you very much, audience, for joining us. Thank you, Professor, for this talk, and see you at some other occasion. Till then, bye-bye. Thank you very much.
Thank you all. Have a good night.
Bye.
Bye.